Okay, let's do some nice calculations. So this is the definition of uniform distribution, right? So you can check that the expected value of x in this case is 1 over, no, a plus b over 2, which is a very natural result because so you have a random variable taking values between a and b, and the density function is just uniform. So you would expect that the expected value will just be the midpoint, right? Just a plus b over 2. But you can check it by integration, right? By a to b, x 1 over b minus a dx. This is going to give you, I think, x squared over 2, right? So b squared minus a squared over 2b minus a, which is going to give you a plus b over 2. And you can also find a formula for variance, etc., etc. And when a equals 0, b equals 1, you call it the standard uniform distribution. So uniform 0, 1 is called standard uniform. Okay. So another example is a very important example, Gaussian. Gaussian a and b, where a is in R and b is a positive number, okay, positive real number. So we say x has the Gaussian distribution with mean a and variance b if and only if its distribution has the following form. E to negative, let's make this strictly positive, okay? 0 to infinity. So x minus b squared, x minus a squared over 2b, 2 pi b dx, and x is in the real line here. So it can take values between minus to plus infinity. And it's, okay, so its shape is something like this. It's centered around a. Okay, so this is the function e to negative x minus a squared over 2b, square root of 2 pi b. So this is called the, so in this case, x is said to have the Gaussian distribution with mean a and variance b. And why do we say it? Because check that expected value of x is a and variance of x is b. If the density function is given this way, you can check by integration is that expected value of x is a, variance of x is b. That's why we say it's with mean a and variance b. In more standard notation, we use mu for a and sigma squared for b. But since we used mu for some measures before, I avoided that notation. And when a is 0, b is 1, in other words, when we look at the Gaussian 0, 1 case, this is called the standard Gaussian. Standard Gaussian. So just for fun, I'd like to check with you that x is in R is 1. In other words, when you integrate this density function from minus to plus infinity, you get 1. Let's try to see why this is the case, because it's not obvious, right? It's not obvious. In the uniform case, it was obvious. This is just dx, right? Just constant times dx. You can integrate it from a to b and see that this area is 1. In the plus 1 case, that was also easy. But here, it's not very trivial. So let's try to see why this is a probability density function. First of all, what you can do is to get rid of your a and b. So you can define z, which is x minus a over square root of b. So x minus mean divided by standard deviation, okay? So this is what you define, but we do it in a change of variable case, okay? So then what you get is that you have e to negative z squared over 2 pi dz, which is the case where a equals 0 and b equals 1, right? So it is just 2 here, not z. And if you look at this function, this is symmetric around this y-axis, right? So it's an even function. So you can see it as 2 times 0 to infinity of the same function. This area is equal to this area. And hopefully they are both 1/2, 1/2. So now let's look at this. Let's call it c, okay, some constant 0 to infinity of this. So the trick is that it is not very easy to evaluate this integral just by looking at this single integral. The trick is that you can square it and make it a double integral, and now it will become easier to calculate. So let's see why. So c squared is what? Let me use x as the dummy variable and y for the dummy variable of the other integral. So it's a square, right? So this times this. So this times this. Or you can see it as a double integral. Minus infinity to plus infinity twice, e to negative x squared plus y squared over 2 divided by 2 pi dx dy. So this is an integration over R2, right? R2, x and y here. This was from 0 to infinity, sorry. 0 to infinity. So this is not the full R2 then. It's an integration over this region, the positive orthant. The positive orthant. So a nicer way to calculate this double integral is to switch coordinates from Cartesian to polar. So let's do it. So we can have an angle from 0 to pi over 2 and radius from 0 to infinity. So in fact, this integral just becomes what? So polar coordinates. So this is dx from 0 to infinity, dy from 0 to infinity. So in the polar coordinates, we're going to have 0 to pi over 2 and 0 to infinity. So this is for the radius, and this is for the angle. Okay? Now what is the radius? Well, radius is just square root of x squared plus y squared. So I can write r squared here. And dx dy becomes what? R dr d theta. Theta is the angle, r is the radius. And if you remember how to switch those coordinates, there is this additional term r dr d theta. So dx dy becomes r dr d theta. It's like a block. So now this is a much easier to calculate integral because we have r dr here and r squared there. So if you define r squared over 2 equals u, what you get is that 2r or r dr is equal to du. So 0 to pi over 2 and d theta. And inside what do we have? 0 to infinity, e to negative u, du. And there is 1 over 2 pi outside somewhere. So what is this integral? It is just 1. 0 to infinity to negative u du is just 1. Therefore, you have just d theta from 0 to pi over 2. So 1 over 2 pi, pi over 2, right? Which gives you 1 over 4. So this implies c equals 1/2. So we're done. 2 times 1/2 is 1. So maybe it was a bit too fast, but this is all calculus, right? Multivariate calculus. So now, from now on, you don't need to worry about why this is a probability density function. It is, we checked it. If you look at the trick that we did here to get rid of the mean and variance parameters, this is actually a general trick, okay? So in general, so let x be Gaussian AB, then if you define z to be x minus a over square root of b, this is Gaussian 0, 1. This is Gaussian 0, 1. So this is sometimes called standardization, okay? If you have x whose parameters are a and b, then you can make a parameter-free version of it, like a standard version of it, just by shifting this and scaling it by the standard deviation. Okay. So let's see why this is the case, right? This is a claim to be checked. Let's show it. So here's how we're going to show it, and this is indeed a general proof technique, or a general technique in probability, okay? So what do we want to show? Z is Gaussian 0, 1. Let's use the characterization of it in the first hour, or from last time. Expected value of f of z is given as f of z e to negative z squared over 2 pi dz minus to plus infinity. So f of z times the distribution. This is the distribution, right? Density times Lebesgue measure. So show this for every f r to r positive bar measurable. Let's check this. So let f be from r to r bar positive be measurable. So now we're going to calculate this quantity, f applied to z, and hopefully at the end of the day we're going to get this expression. So let's start. First of all, this z is defined in terms of x, whose distribution we know. So we're not sure if z has this distribution, but we know, we're given that x has this distribution. So we can use the fact that z is defined in terms of x and the other fact that we know the distribution of x. So in fact, I can see it as g of x, where g of x is defined as f of x minus a over square root of b. So since we know the distribution of x, this is really g of x times the distribution of x. And of course, g is a function that we just made up. So this is, in fact, x minus a over square root of b. This is what we know, and this is where we're trying to reach. How can we do that? So there is f of x minus a over square root of b, and there is f of z here. So this is telling it itself. Just make a change of variables. Let this be z, and then you're going to get this, hopefully. So let's make this change of variable. Z equals x minus a over square root of b. So then, what do we get? Minus infinity to plus infinity, f of z, e to negative. So this is z squared over 2. Then what is dx? Dx is square root of b dz. Square root of b dz. So dx becomes dz times square root of b divided by square root of 2 pi b. So the b's go away, and we get the desired result. And since we have this for every positive measurable f, we can conclude that the distribution of z is Gaussian 0, 1. So since this holds for every positive measurable f, we conclude that this part is indeed the distribution of z. In other words, z is Gaussian 0, 1. So we use this characterization of being a distribution for a random variable many times. We use it here because we use the distribution of x. And then we use it here. I mean, the conclusion is that this is equal to this for every f. Therefore, we conclude z has a distribution Gaussian 0, 1. So maybe another important random variable, which is positive valued. Exponential. Okay, so we say x has the exponential distribution with parameter c if its distribution is given by c e to negative cx dx for positive x. For positive x. So in this case, it is not very difficult to check 0 to infinity of this gives you 1. You can just make a substitution, or you can directly integrate it, I guess, and then evaluate it from 0 to infinity. What is more interesting is the expected value and variance. So what is the expected value? X times the distribution from 0 to infinity. So how can you evaluate this integral? X times c e to negative cx dx. X times an exponential function, right? How would you integrate it? By parts, right? So let's do by parts. Let's call x maybe u, and the rest dv, so that v is what? E to negative, negative e to negative cx. Right? So then this is u times v, so this is x times negative x times e to negative cx from 0 to infinity, minus 0 to infinity, v, which makes it a plus, du, which is dx. So I'm leaving the first part as an exercise for you. So you need to evaluate the limit as this goes, as x goes to infinity, etc., etc. So this part is just 0, okay? Just check. And this part will give you what? What is the result of this part? 1 over c. Well, you can just integrate it, right? Or here's what you can do. c times 1. And now this is a probability density function. So you know from 0 to infinity, this integral will give you 1. So the result is 1 over c. And you can do a similar calculation for variance. So first expected value of x squared, and then calculate variance. You're going to get 1 over c squared. Okay. Any questions so far? So this exponential distribution is indeed part of a member of a larger family of distributions called gamma distributions. Okay? So let's also talk about the general family. So we have A and C. Okay? So we say X has the gamma distribution with parameters A and C. So this A is called shape index, and C is called the scale parameter. So the C part is really coming from the exponential. So this starts like an exponential. So x dx is given by, okay. So it starts like an exponential. Okay, then cx to power a minus 1. So when a equals 1, you don't have this part. Divided by some number which only depends on a, and which makes sure that this is a probability density function, dx for positive x. So here, gamma is the gamma function defined by zero to infinity, e to negative x, x to a minus 1 dx. So that when you integrate this quantity from 0 to infinity, you get 1. So with this definition, just check that the integral or the probability that x is in R plus is just 1. The integral of this from 0 to infinity is just 1. And you can also calculate expected value and variance. So this is a over c instead of 1 over c. So in the exponential, it was 1 over c. And in the general case, it is a over c. And the variance is a over c squared. Okay. So here are some, maybe before talking about special gamma distributions, including the exponential, maybe we should list some special properties of the gamma function, not the distribution. Okay. So some properties of the gamma function, not the distribution. Okay. First of all, what is gamma of 1? Well, gamma of 1 is just 0 to infinity, e to negative x dx. Therefore, it is 1. Okay. What is nice is that when you try to calculate gamma of a plus 1, this is equal to a times gamma of a. So it's a recursive formula. And this you can check or prove by integration by parts. So this is going to have an integral with here a plus 1 minus 1. And for a, it's going to have just a minus 1. So when you do the integration by parts in the correct way, you're just going to reduce this power of x by 1, and you're going to get this gamma a part. Okay? So it's a boring exercise, so I skip it. Okay? But the nice thing about this recursive formula is that starting with gamma of 1, you can calculate gamma of 2, gamma of 3, etc. So let's calculate gamma of 2. So this is gamma 1 plus 1. So this is 1 times gamma of 1, which is 1. Gamma of 3. So this is gamma of 2 plus 1. Therefore, it's 2 times gamma of 2. So this is 2 times 1. So gamma of 4 is 3 times gamma of 3. So it is 3, 2, 1. So you get the idea, right? Gamma of n is n minus 1 factorial, for n being one of 1, 2, 3. So here are some special gamma distributions. Okay. So if A is 1 and C is just arbitrary, we have gamma 1 and C. This is the exponential C. Okay. When A is an integer, like here, so A n is one of 1, 2, 3, and C is positive. So we have gamma n C. So this is sometimes called the Erlang distribution with, again, the same parameters, just a special case name. Okay. And when A equals n over 2 for some integer n, and C is 1/2, so this gamma n over 2, 1 over 2, is called the chi-squared distribution. Chi-squared distribution with degrees of freedom n. Bilinear combinations of what? Gammas?
Gamma or Gaussian both?
Yes, but they usually require, well, first of all, in the previous example, we did not take a linear combination. We just looked at one random variable and scaled it and shifted it. Okay?
Yeah, I know.
So, but there are results, for instance, of the following form. Let's say you have some gamma random variables with the same scale parameter. And then if you add two such gamma random variables, you again get a gamma random variable, provided that they are independent. So since we haven't talked about independence yet, we do not discuss such results. Okay? But there are certain scaling properties of gamma. I think there is even one in the next homework. So there is some scaling property about gamma. What I'd like to discuss with you is connection with Gaussians and gammas, and in particular the chi-square distribution. So in many courses in statistics, you must have discussed at some point the chi-square distribution. Okay, so if you have taken a course in statistics, for sure there is at some point a discussion on chi-square distribution. And chi-square distribution is about really squares of what? Squares of Gaussians. So the connection between Gaussians and chi-squares is the following. We're going to prove it now, just for the case n equals 1, between Gaussian and chi-square 1. And maybe I should say Gaussian 0, 1 and chi-square 1. So here's the result. It's very simple to state. So let Z be Gaussian 0, 1. Then Z square is chi-square with degrees of freedom 1, meaning that it is gamma 1/2, 1/2. Okay? Well, how can we prove it? Well, we can prove it in a similar way. We solved our exercise, right? In the Gaussian case. So what we're going to do is to take a function of Z square. So let f be a positive measurable function. And let us calculate f of Z squared. Well, Z square is the thing in question, right? We don't know the distribution of Z square. We know the distribution of Z. So let's use the distribution of Z. We can see it as G of Z, where G of Z is defined as f of Z squared. So now I can calculate it because I know the distribution of Z. It is G of Z e to negative Z squared over 2 over 2 pi, square root of 2 pi, dz, minus to plus infinity. And now let's use the fact that this was just f of Z squared. Well, at the end of the day, we want something like this, f of Z times something dz. So let's make the argument of f just Z. Or maybe I should use another dummy variable. Let's call it y, OK? So let Z squared be y, so that 2z dz is dy. Or dz is dy over 2 square root of z. 2 square root of y. OK, so maybe before doing that, I should have passed to 2 times 0 to infinity first, because that's an even function, right? There is Z square here, Z square here, so I can do it. Let's do it first. So now we can do this change of variables. It's 1 to 1 now. So Z is going from 0 to infinity, if and only if y is going from 0 to infinity. So this is 2 times 0 to infinity f of y e to negative y over 2, square root of 2 pi, and dz is dy over 1 over 2 square root of y. Okay, so we're almost done, because we have f of y times something. Let me put the 2 here. So this is a probability density function for sure. We just need to reorganize it to see that it is gamma. Okay? How does the gamma distribution look like? Let's recall. This is how it looks like. So whatever we have in the exponential part, we should have it in front of the exponential part, and we should have the same parameter raised to some other power. So let's try to make it this way, make it look this way. So 0 to infinity f of y, now what? E to negative y over 2, right? So I need to multiply it by 1 over 2. And then I should have 1 over 2y raised to some power. Which power? Let's look at the power of y here. It is minus 1 over 2, right? The power of y here is minus 1 over 2. Therefore, it should be 1 over 2 minus 1. In the form we want. In the form we want, a minus 1. And whatever we have here, whatever left for the denominator, is going to be gamma of 1/2. This is the A, right? This is A, and this is C. Gamma 1/2, 1/2. So whatever left for here is going to be gamma of 1/2 dy. In particular, gamma of 1/2 is square root of pi. This is what is left for the denominator. So we show two things. One thing is that this z square has the gamma distribution with 1/2, 1/2 parameters, plus, since it has to be gamma, it is already in the form of gamma, the denominator can only be gamma of 1/2. Otherwise, this cannot be a probability density function. So for this to be gamma 1/2, I must have that gamma 1/2 equals square root of pi. So that's also, as a byproduct, we proved that gamma of 1/2 is square root of pi. So you can add it to your list of special properties of gamma function, right? Let's add it to here. Gamma 1/2 is square root of pi. So you can also calculate gamma 3/2, gamma 5/2, etc. using this recursive formula. So what we showed is that z squared is a gamma random variable with parameters 1/2, 1/2. So z squared is gamma 1/2, 1/2 is the conclusion. Okay, another example. Another continuous random variable, okay? So let's say x is Cauchy, let's say standard Cauchy, if and only if the distribution of x is of the following form: pi times 1 plus x squared dx, x in the real line. So this is the density function of a Cauchy distributed random variable. So why do we discuss Cauchy at all? Because it's a weird distribution. Okay, let me wait for a moment, and then we're going to discuss what is weird about Cauchy. Anybody who knows what is weird about Cauchy? Okay. The weird thing about Cauchy is that it doesn't have an expectation. So let's calculate expected value of x plus. That's a numerical random variable, right? Can take plus and minus values. So the definition of expectation is what? Expected value of x plus minus expected value of x minus. So expected value of x plus is what? So you need to integrate it from 0 to infinity. X times this. Because x plus is 0 on the rest of the real line. From minus infinity to 0, x plus is just 0. So this is this integral. And in fact, this is even equal to x minus. Because x minus, for x minus, you have minus infinity to 0, minus x, 1 over pi, 1 plus x squared dx. And just by switching to, just by a simple change of variables, if you just call it the new x, the two integrals are just the same. The thing is that this integral does not converge. So you have an infinity minus infinity case. So expected value of x does not exist. In the second half of the course, we're going to see some connections of Gaussian distributions with this Cauchy distribution. So right now it is just up in the air, but later it's going to have some connections with other random variables, with uniforms, with Gaussians, etc. So okay, that is the end of my examples for continuous random variables. But before finishing the lecture today, I'd like to discuss with you an example of a random variable which is neither discrete nor continuous. And the construction of this is super easy. So it's not going to be like a pushed example, like an example that I tried to make up myself. So it's going to appear very naturally, okay? So neither discrete nor continuous. So let's say we have a random variable z, which is Gaussian 0, 1. And let's say we have an event A such that its probability is strictly between 0 and 1. So the probability of A is strictly positive. The probability of A complement is strictly positive. Let's look at Z over the set A. This is our random variable. So this means what? Y of omega is equal to Z of omega if omega is in A. Otherwise, it's 0. So just a Gaussian 0, 1 random variable restricted to a set. And outside that set, it's just 0. Okay? First of all, let's show y is not continuous. Well, if you look at the probability that y equals 0, if you look at the probability that y equals 0, so this 0 can come from this part or from this part. So the z itself can attain the value 0, but outside the set A, we already have that value 0. So for sure, this is a superset of A complement. Right? If omega is in A complement, y is 0. Right? This is a subset of this. Therefore, we have this relation. And this is strictly positive because we assume probability A is strictly below 1. So this means the distribution has an atom. We have the Lebesgue measure at 0 is 0, but probability that y equals 0 is not. So this is a contradiction to absolute continuity. So we cannot have the distribution absolutely continuous with respect to Lebesgue. So not continuous. The next thing is that y is not discrete. Okay. So in other words, we're going to show that there is no countable set in which y takes values in with probability 1. Okay? So let's look at every singleton. Okay? First, look at a singleton that is different from 0. Okay? 0 is a special case. So let's look at some possible value. So the probability that y equals z is what? So y can take this probability only in the event A. Only in the event A. So we are in, so z takes this certain value, and we are in A. This is if and only if. If y equals little z, and z is non-zero, this means we must be in the set A, and z must take this value little z. Conversely, if z is equal to little z and we are in A, we are in this case, therefore y of omega equals little z. So this is if and only if. And this is smaller than probability of A. Sorry, this is smaller than probability that z equals little z, which is 0, because z is a continuous random variable. Z is Gaussian 0, 1. So a probability less equals 0 means the probability is 0. Let's look at z equals 0. What I'd like to argue is that this is strictly less than 1. So you have z equals 0, for which the probability is strictly below 1, and for every other z, you have y equals z equals 0. So this means you cannot form a countable set. You cannot form a set of singletons in which y takes values with probability 1. That's what we're trying to argue. Let's argue for probability y equals 0 is less than 1. Okay? First of all, probability y equals 0 can happen in two cases, right? So either z equals 0 and we are in A, or we are in A complement. Well, this is less than probability of z equals 0 plus probability of A complement, right? Probability z equals 0 and A is a subset of the event that z equals 0. And this is just 0 plus probability of A complement, which is strictly below 1. So we showed that the probability that y takes the value 0 is strictly below 1. So y is not discrete. So all we did is to multiply a continuous random variable with an indicator function. So it's not a very difficult operation, right? It should work very nicely, right? So, and we should have a theory for such random variables, right? A continuous random variable restricted on a set. So it is a very natural random variable. So that's why we don't want to restrict ourselves to discrete case and the continuous case. Okay? We should be able to deal with things in between, such as this. Okay. So thank you, and see you next week. I think we have only a little to discuss.